Section 3.7 is all about optimization problems, which means we're going to be given a question and we want to minimize something or maximize something. So this is actually a great application used in the real world all the time to minimize or maximize something. So that's our only objective. I've broken this into two videos, one where I do the practice with you and one where you do the practice on your own, and then basically I'm just going to reveal the answer. I'm not even really going to talk through it. That second video will be if you have questions on any of those once I reveal the answers. That's something to talk to me about in Teams or OneNote. So essentially here's what we're going to do. We're going to read the question and we're going to identify anything that we're given and anything that we need to figure out. If possible, make a sketch. I usually do make a sketch because it does help me to visualize the question. Then I'm going to write the primary equation. So in the question, it's going to say find the minimum cost or find the maximum area or something. That's your primary equation. Keep in mind, you might have to Google equations. If you don't remember, this is how to find the volume of a cylinder. It's also in the back of your calculus textbook if you bought the actual text. Then we want to reduce that primary equation to having a single independent variable. So we might have to have a secondary equation that helps us to, do some substitution and that sort of thing. We talk about the feasible domain, what would make sense in the question if we're talking about, say, an area or a volume. Then a negative length wouldn't make sense. So that's what I talk about with a feasible domain, what makes sense in the question. And then we're going to determine the desired min or max using calculus. Oh, hey, min, max, we already know how to find those using, say, critical values and whatnot. So let's just dive right in. This first example, I go through little baby steps at a time. So this first example is pretty straightforward, but I wanted to use a simple example to go through the steps that we typically would go through. So we have two non-negative numbers. So again, that's going to help us when we talk about the domain. The non-negative numbers tells me that I can't have a negative number, whose sum is 9, and the product of one number and the square of another number is a maximum. So I have two things going on here. I have the quantities that I know and the quantities to be determined are I need to determine x and I need to determine y because those are the two non-negative numbers I'm determining. Those are the quantities. The primary equation has to do with what's being minimized or maximized. So it tells me that I'm looking for the product of one number and the square of another number to be a maximum. So notice I've written that as x squared y equals p. Keep in mind that it doesn't matter which one's x and which one's y. So some people might say, well, what if I did xy squared equals p? Yeah, it's the exact same thing, guys, because we're just looking for two numbers. So here's what I'm trying to minimize or maximize. And notice I have whose sum is 9 I haven't used yet. So that's what we're going to call a secondary equation. That's going to help me get this guy down to just one variable. So again, reduce the primary equation to having a single independent variable, which might use a secondary equation. So this is a great secondary equation. Their sum of the two numbers, the first and the second, is 9. And then I just isolated y, and I could have isolated either one. Notice I isolated y on this one because I didn't want to have to FOIL a binomial x squared, so I just made it easy on myself. Replace y in the equation with 9 minus x, and then simplify. So this is still my primary equation. But notice now it is instead of written like this with two variables, I now have it written with one variable with the help of my secondary equation. So what's my feasible domain? And here sometimes we're just guessing. On this one it's not so much a guess. We know that if their sum is 9 and neither one of them is negative, that at the least they have to be 0 and at the most they have to be 9. So it's between 0 and 9. So that feasible domain, along with what I'm going to find, which is the critical value, is going to help me find the min or max. So again, notice here I used 0 as my left-hand side and I used 9 as my right-hand side. That's what I want to do with my feasible domain. Then I'm going to take, this was my equation, primary, written with just one variable. Notice I have found the primary equation derivative, because of course that's going to help me find my critical values, 0 and 6. So 0, 6, and 9, of course, are the values that I'm going to use. And notice I've just made my table like I normally do, used a test point, found positive and negative. Remember, I'm looking for a max, so if I have an increasing function to a decreasing function, that is a max. So my max occurs at 6, and then I can plug that back in and say x plus y equals 9, and x is 6, so 6 plus y equals 9. That means that y must be 3. Now, when I answer the question, I don't need to say x is 6 and y is 3. I can say the two non-negative numbers whose sum is 9 and yields a maximum product of one number and the square of the other is 6 and 3. So I didn't even need to include x equals and y equals. I could just say 6 and 3. Now we're going to go through two examples together that aren't broken down quite that much, and I'll talk through as much as I can without making this a 30-minute video. I'll do my best. So here we have a rectangular pen with 3 parallel partitions using 500 feet of fencing. It's best if you can come up with a picture. So I've got a rectangular pen and it's 3 parallel partitions. So I could have done this, but obviously, as we all know, if I want to use as little fencing as possible, I'm going to do this. So this is about what it's going to look like. And we'll call this X and we'll call this Y. So if I'm trying to maximize the total area of the pen, what function will I use? Well, it's a rectangle, so area is just going to be xy. So here's what my picture looks like, the official picture that we're going to use. And notice there I've just labeled that each of these is x, and that's to help me to come up with my secondary equation, which says I'm using 500 total feet of fencing. So if I'm using 500 feet of fencing, and I have 1, 2, 3, 4 x's, and I have 1, 2 y's, then it would make sense that this would be a secondary equation. Now, what have I done with that equation? I have isolated it so that either x or y is all by itself. And it doesn't matter which one. I could have just as easily found x by itself. Now I go back to my primary equation, which of course is what I'm trying to maximize. And what am I going to do? I'm going to replace y with what y is equal to. So again, I've shown that work here. Once I've done that, then I find the derivative of that. So the derivative got me down to x equals 62.5, excuse me. So 62.5 is a critical value or critical number. Now I need to find my endpoints. So really, what am I going to use for my endpoints? I'm going to use 0 and 125. So why did I choose 125? Was that random? Well, essentially I said this. I said, let's pretend y is 0 and just, look at what 4 x's. 4 x's have to equal 500. So the very, very max it could be is 125. And could it really be 125? No, not quite. But there's no really exact way to do it. So just do something that makes sense and go with it. Now from here, what am I going to do? I've got my values. I used my test points. And again, this is increasing. This is decreasing. So this is going to be a max. So my max area is going to happen at 62.5 feet. How do I know what y is? Well, then I have to plug it back into my function, and I find out that y is in fact 125. So the dimensions to maximize the area are 62.5 by 125. One more for us to work through together, but remember the next 4 examples that we do, I'm really not going to talk through them very much. So if you want to try one where then I go through and each part step by step, this would be a good one to press pause, try this question, then press play to see how you did. So here I have an open rectangular box with a square base made from 48 square feet of material. So I've got a rectangular box, but the base is square. So I got to make a square-ish, and it's going to look something like this. Again, you don't have to be a good artist. I'm certainly not. But it's going to look something like that. And I know that it has a square base, which means these guys are both the same. So x and x, we'll call it. And then I don't know the height, but it doesn't say it's a square prism. So the y value could be different than the x. I'm trying to maximize volume. So remember, volume of a cube is base or length times width times height. And so using my picture, x times y, or x squared y, that's my maximum. Again, I have two variables. That's no good. I need just one variable. So how am I going to get a secondary equation? Well, I can look at surface area. This is given to me and I haven't used it yet. So again, surface area might be something where you don't remember and you have to go to your textbook or something to find the answer. But let me talk through where this came from. This area of this square at the bottom is x times x, or x squared. And then I have 4 equal parts that look like this. So 4 of them that are x units by y units, 4xy. That's the total surface area that should add to 48 square feet of material. So again, I'm going to try to get a variable all by itself, which I have done. And then I have to go back to my primary equation and plug in that y value, x squared y. And then remember, it's just algebra to here. From here, now it's calculus. From here, now I have to actually find the derivative of the function. Then plug in a 0 to find my critical values. And I end up with plus or minus 4. So plus or minus 4 is what I'm going to be dealing with. Does negative 4 really make sense? No, I can't have a negative length of my prism, or my rectangular prism, I think they're called, yes. So now what? Well, now I have to use whatever I believe to be the right endpoint, as well as, of course, 4. And so obviously it can't be less than 0 because we're dealing with the length of a side. And for radical 3, again, I've tried plugging in 0 for y again to get some value for x. So I'm using 4 radical 3 for my upper bound. Find some kind of value that's in the test point area between the intervals. And again, I get positive to negative. And that makes me happy because that means I have a maximum, and that's what I'm trying to do, is maximize the volume. So 4 is the max. I'm going to plug it back into my function and find that y is 48. I'm sorry, that y is 2. And so the dimensions to maximize the volume of the box are 4 by 4 by 2. Here are 4 questions for you to work on. And I don't take this lightly. I know these take a really long time to do. So what I'd like you to do is, these are really good practice. I would suggest taking a screenshot of this and just working through all 4 problems. In our next video, we are going to do all 4 questions, but as I told you, I'm not going to go through them in as much detail because otherwise it's just going to be another really, really long video. I'll do my best to give you as much info as possible, but again, I'm not going to take you through how do I find the derivative. We know how to do those things already. So go ahead and try all 4 of these questions, and in the next video, I'm going to go through all 4 of these questions.